For decades, automotive design has forced a harsh compromise. If you want a lightweight, corner-carving sports car, you sacrifice off-road clearance. If you build a rugged, boulder-crawling buggy, you give up highway speed. And if you want a heavy, insulated luxury lounge, you surrender agility. Merging extreme speed, rugged terrain capability, and premium quietness into a single chassis presents a series of competing physical demands. Speed requires low mass and a low center of gravity. Off-road durability demands high articulation and heavy-duty components. Luxury requires thousands of pounds of dense sound deadening. These requirements pull the design in three different directions. This custom Ram architecture addresses those contradictions simultaneously. Look at the profile. The massive, deeply grooved off-road tires and lifted suspension are built for low-speed utility, yet attached to a frame intended to move like a touring car. Which brings us to a specific engineering puzzle. How does a 6,000-pound, high-riding block of steel and leather actually function when pushed to extreme environmental limits? To find out, we have to look past the paint job and run this architecture through a series of physical stress tests. Leaving the hostile exterior behind, we drop into the highly refined, leather-stitched interior cabin. This environment is built to combat the primary byproduct of heavy utility vehicles, NVH, which stands for noise, vibration, and harshness. It is the mechanical strain transmitted from the road to the occupant. This wireframe illustrates the first line of defense. Thick, multi-laminated acoustic glass seals the perimeter, while an active electronic noise cancellation system monitors the cabin. When the deep, low-frequency roar of the engine attempts to penetrate the firewall, the system broadcasts precise inverse audio waves to neutralize the sound before it ever reaches the driver. But sound is only half the battle. To stop physical vibrations traveling up from the heavy axles, the interior architecture serves as a mechanical buffer. The dense memory foam in the seats and the heavy layered materials backing the dashboard act as targeted acoustic dampeners, physically absorbing kinetic energy. The result is a sensory disconnect. While thousands of controlled fuel ignitions happen under the hood, the interior is tuned to maintain a quiet, stable atmosphere. Maintaining this degree of stillness in a high-impact environment relies on the interior functioning as a high-density buffer against the forces of the road. Taking this high-clearance chassis out onto the open highway introduces a completely different set of physical forces. Massive, deep-tread mud tires are designed for low-speed grip. When you push them past 70 miles per hour, the rubber begins to stretch under centrifugal force. In a standard vehicle, this creates violent vibrations that can compromise stability. Compounding that friction is the aerodynamic penalty. Pushing a lifted, structurally blocky SUV through the atmosphere is like trying to force a vertical wall through a headwind. The only way to move that volume of air and overcome the massive rolling resistance of the tires is through continuous engine torque. The drivetrain must deliver enough horsepower to the axles to counteract both air resistance and friction. Highway cruising in a heavy-duty rig is a mechanical contest. It is a constant application of power to overcome the drag and resistance generated by the vehicle's own scale. Take the vehicle off the asphalt and into shifting desert dunes or deep jungle mud, and the requirements for power delivery change instantly. In soft terrain, raw power can be a liability. Mechanical energy always takes the path of least resistance. If one wheel loses grip, all power rushes to that slipping wheel, spinning wildly and digging the heavy frame straight down into the dirt. This top-down schematic shows the countermeasure preventing that sinkage: highly responsive torque vectoring. It allows power leaving the engine to be split unevenly and distributed directly to the wheels that have the most traction. Onboard computers read the terrain resistance at the wheels thousands of times per second. The millisecond a tire begins to slip, the system reduces power to it and instantly routes map torque to the tires anchored in solid ground. When the mud gets deep, mechanical locking differentials engage, physically binding the axles together. This forces those massive 35-inch tires to rotate in absolute unison, allowing the engine to drag the 6,000-pound frame out of uneven ruts. Simultaneously, the adaptive damping suspension continuously adjusts its vertical travel. If a wheel drops into a sudden crater, the strut instantly adjusts its resistance to keep the heavy steel chassis level. Conquering extreme off-road environments is a victory of data management. It relies on high-speed computational processing to manage mechanical output in an unpredictable environment. Bringing the vehicle back to a standstill, we can look at the mechanical forces it just managed: drag, thermal stress, and traction loss. It handled these different environments while keeping the driver in a climate-controlled, acoustically shielded cabin. Machines developed with this level of integration show a point in automotive engineering where sensor data and material science allow a single platform to handle a wider range of physical stresses than was previously possible. The distinction between a utility truck and a luxury car has faded. By applying advanced software to heavy-duty hardware, engineers have created a machine that handles the high-speed highway and the deep trail without compromising its composure.